For this lesson, we're going to start with a topic that should be a review for most of you, and that is something we covered in the grade 10 course, which is transformations. And we're going to start off with the familiar quadratic relation. So transformations of a quadratic. In vertex form, that's the easiest way to talk about transformations because the transformation ties in directly with the vertex. So if you were presented with this generic vertex form equation of a quadratic, what are the possible transformations reading from left to right? If you become very good with and very familiar with transformations, you don't actually have to do it this way. You don't have to be constrained to reading it from left to right. But it certainly is the most straightforward way to handle it. And so that's how we're going to be focusing on it in this course. So reading from left to right, the first thing that I run into is the value of A. And the value of A is going to possibly tell me about reflections, and the value of A is going to also tell me about, and I should say more than scaling, it tells me about vertical scaling, and vertical scaling could mean a stretch or it could mean a compression. So all of that is tied up into that single A parameter. Then we get to, so this was our first from left to right. Our second from left to right is the H value. And just as a reminder, that is the X coordinate of the vertex. And what that tells us is the shift, the horizontal shift either left or right. And then finally, our third value is the K value, which is the Y coordinate of the vertex. And that tells us the vertical shift. Which would be up or down. So we have, and when I say, again, I should have put this in here, that's going to be vertical reflections, or a vertical reflection. So this tells me if I have a vertical reflection, and it also describes any vertical scaling, which would be a stretch or a compression. The H value gives me my horizontal shift left to right. My K value gives me my vertical shift up or down. And you can see I've summarized that here. Now, a little bit more detail. Vertical reflections are going to occur if the A value is negative. If the A value is positive, there's no reflection. The vertical scaling is going to depend on the value of the A. If A is equal to 1, then there's no scaling. Vertical scaling is only going to occur when the A is not equal to 1 or is not equal to negative 1. If the A value is large, and the best way to describe the size or the largeness of the A value is here, using actually the absolute value notation. So if the absolute value of A is equal to 1, then we have no scaling. If the absolute value of A is greater than 1, so that means numbers either bigger than 1 or less than negative 1. So if we think about the number line, so there's 0, there's 1, and there's negative 1. If we look at this number line, then these values, so these values of 1 and negative 1 would be no scaling. If I'm out here, then that means I have a stretch. And if I'm in between negative 1 and positive 1, then I have a compression. Then we have what's known as a horizontal translation. That's the shifting left or right by some value h, and a vertical translation to shift up or down by some value k. it's good to work with the familiar, or at least think about the familiar. And in this case, the familiar is the idea of starting with a parabola that is at the origin. So that is just y equals x squared. And then imagining, in particular, what the h and k moving the vertex, what that's going to do to the overall graph. So try to keep that image in mind as we move forward with this. Okay, now another thing we've introduced in this unit is the idea of function notation. So the simple equation y equals x squared, if we were graphing it, would be y equals f of x. And so the transformation of x squared through the a, h, and k values becomes a transformation of the function. Now I want to make this part clear. That's why I've got a little bit of work that I'm going to do here. If we can make this connection between the transformations on a parabola and the transformations using function notation, well, that means that we can represent the transformations, these same types of transformations, on any type of function. So let's start off with the parent function of a parabola, which is x squared. So f of x equals x squared. Now, the order that I bring these transformations in is important. I'm going to start inside the function bracket. There are other ways to do this. Actually, you know what? Let's do them in order from left to right, because there's a big emphasis on doing things from left to right. So how would I introduce a multiplication by this factor a? Well, what I would do is I would start off, I would multiply both sides by a. And so for the left side, I get a multiplied by f of x. And the right side, I get ax squared. Now, reading from left to right, the next thing I have is, instead of x, I want to replace x with x minus h. So I now get a f of bracket, but instead of x, I'm going to actually write x minus h. That's equal to a, and instead of just x squared, I'm going to get something else squared. But what is that? It used to be x squared, now it's going to be x minus h all squared. And then finally, I have to add k, but notice that adding the k occurs outside of this term, which is all this multiplication and exponents. So I get af, why is it not blue? Sorry, I'm being picky for this. There we go. af of x minus h is equal to a bracket x minus h all squared. That's what we had the line above. And so to introduce a k here is to introduce a k here. And so as you can see, that makes sense. So this function notation applies perfectly well to the quadratic expression, so long as, of course, the function is defined as a quadratic. All right, so if that's the case, let's stop talking specifically about the quadratic function, and let's just start talking in terms of generalities. So if we start off with some generic function that has a graph y equals f of x, if we transform it so that the new graph is y equals f of x plus 1 plus 3, as written here, then what are the transformations? So we're going to start reading from left to right, and the first transformation that I run into is right there, and the second transformation I run into is there. And I think of this in terms of quadratics. This first transformation would be a horizontal shift, and keeping in mind the meaning, if this were a vertex, if this was x plus 1 in the quadratic equation, this would mean a shift to the left by 1. So this is a horizontal shift left by 1. And then we get to transformation number 2. This is vertical, a vertical shift. And this time now, plus here would mean up. So this is a vertical shift up by 3. All right, let's carry on. So let's go back to our quadratic, but instead, let's not think of it in terms of vertex form. Let's think of it in terms of transformations. So this dotted line, or the dashed line that I have here, here is the parent function y equals x squared, or f of x equals x squared. Well, if this has two transformations, the first transformation is left 1, and the second transformation is up 3, then I can take every single point. So let's find some good points on this graph. There's one at the origin. There's one here at 1, 1. There's one here at 2, 4. There's one here at 3, 9. And then there are symmetric points matching. All right, so I have a lot of points to choose from. So let's go ahead and transform those. I'll transform them in a different color. So left by 1, there's one step over to the left, and up by 3. 1, 2, 3. So there is my first point. Since I'm moving to the left, let's take care of these ones over on the left side. So here I am at negative 1, 1, left by 1, up by 1, 2, 3. That actually overlaps with a point we've already got. I'll take that blue point that's underneath there, left by 1, up by 1, 2, 3. Out here we have negative 3, positive 9, that's the point. Left by 1, up by 1, 2, oh, that's off our graph. I can't do anything with that. Okay, what about here at 1, 1? Left by 1, up by 1, 2, 3. Left by 1, up by 1, 2, 3. And just as happened with the other point, this one is going to go off the graph vertically, so I'm not going to deal with that. And I'm going to try to get through these points best I can and draw my parabola. So I end up with that. Another thing you can do is you can actually just do this directly on the coordinates of the points. So if we start with the point 0, 0, what does it mean to take the point 0, 0 and move it left by 1, which was transformation number 1? Well, to move left, don't forget this is x and y, so left would be the x, so that moves this x to negative 1. And then what happens when I move this point up by 3? Well, the x coordinate doesn't change, but now the y coordinate goes up by 3, and I get that. Or you can do this all in one step. Let's take the point 1, 1, and let's just move it left by 1, which would take it to 0, up by 3, which would take it to 4. The point negative 1, 3, well, that's this one. And the point 0, 4, well, and that's this one. So you can do this a number of ways. And I illustrate that further because now, what if the parent function is actually just a set of ordered pairs? So essentially a set of points. There's an x, there's a y, there's an x, there's a y, there's an x, there's a y. So our transformations, transformation number 1 is left by 1, and that's going to affect the x because it's left right. Transformation number 2 is up by 3, and that's going to affect the y. And so the point 1, 2 becomes, and again I'll do this in two steps, 1, 2, so we take the x coordinate left by 1, that becomes 0, 2, which then becomes 0, 5 as I go up by 3. So there's transformation 1, there's transformation 2. 2, negative 3, when I move that to the left, that becomes 1, negative 3. And when I move that up by 3, that becomes 1, 0. And finally, negative 5, 7. Move that to the left, becomes negative 6, 7. And move that up by 3, that becomes negative 6, 10. And so now my actual answer would be the new set of points. So f of x plus 1 plus 3 is equal to the set of points 0, 5, 1, 0, negative 6, 10. So in this case, we only had 3 points to start with. We've transformed them, 3 ending points. Now we have the radical function. This is one of the new graphs that we've introduced. Square root is familiar enough, but the graph of square root might be new to you. Just as we did with the parabola, we're going to try to identify some good points on the graph to start with. And I've got some to choose from. So I have those points to choose from. As it turns out, the points that I've chosen are 0, 0, 1, 1, 4, 2, and 9, 3. So let's go ahead and do this one, kind of combining what we did before. 0, 0 turns into, so left 1, that takes it to negative 1, up by 3. 1, 1 becomes 0, 4. Left by 1 takes this to 0, up by 3. 4, 2, left by 1 turns that into 3, up by 3 turns that into 5. And 9, 3, left by 1 turns that into 8, up by 3 turns that into 6. And we could have done that straight with the points as well. So we now have a point at negative 1, positive 3. So that's taking this point, left 1, up 3. This point, left 1, up 3. This point, left 1, up 3. And this point, left 1, up 3. And we end up with a graph that looks like that. It's not perfect, but we're doing this freehand. And as I've mentioned before, the radical function looks like a part of a parabola that's been turned onto its side. All right, another one of the new functions that we've been looking at is the reciprocal function. Now this one is interesting. I'm going to start with points, and then I'm going to shift to something a little bit more abstract. So if we start with points, we can see a couple of well-defined points here, but it's really not enough to work with. So this has the point 1, 1, and this is the point negative 1, negative 1. So we can transform those, but it's really not enough. I could also transform these points that are on the halves. So we started, so quite obviously we have the point 1, 1. We have negative 1, negative 1. I could stretch that to the point 2, 0.5, and 0.52, which is here. And I could also stretch that to negative 2, negative 0.5, and negative 0.5, negative 2. So I could do it this way, and it will work just fine. But there's another thing I could do here, which is to remember that I've got these asymptotes. So I want to keep in mind that I have a vertical asymptote at, and this vertical asymptote is x equals 0. I have a horizontal asymptote at y equals 0. And let's focus on those as a matter of fact. So the vertical asymptote at x equals 0, well, what kind of transformation affects this vertical line? The type of transformation to affect this vertical line would be a horizontal transformation, something that shifts it to the left or to the right. And so in this case, we have a shift left by 1. So that's actually going to move the asymptote here. So x equals 0 shifts over to x equals negative 1. And my horizontal asymptote is going to be affected by a vertical shift. Well, that's shifted up by 3. So y equals 0 turns into y equals 3. And that moves this asymptote to here. And now I can take the easiest of these points, which would be 1, 1, for example. I'm going to go to the left by 1 and up by 1 to 3, which gives me a point there. Negative 1, negative 1, to the left by 1 and up by 3, which gives me a point there. And now I just need to sketch in the rest. We're not trying to be super precise. We just want to get a good idea of what this is supposed to look like. And so we end up with the overall shape stays the same. I do find the reciprocal function is the most challenging to do in this regard. You can do an okay sketch, but you're never going to get a whole lot of precision. Drawing asymptotes or drawing lines that approach asymptotes freehand is actually much more challenging than you might think. Like even here, I didn't do a great job of it. I'll give it one more attempt to clean that up. That's a little bit better, still not perfect. So don't overlook transformations on the asymptotes. The asymptotes are, in the case of, well, basically anytime you have a function with asymptotes, the asymptotes are essentially the most important feature of that function. All right, so now going a little further, I've got the radical or square root function, but my transformations are different. So let's take a look at that equation. Y equals 2 f of x plus 3. And my first transformation that I run into is there. My second transformation I run into is there. My first transformation is the a value, which is equal to 2. And this means I have a vertical, and in this case it is a stretch, a vertical stretch by 2. That means I'm going to take all of my y coordinates and multiply them by 2. And then my second transformation is going to be, it's also vertical, but this one's going to be a vertical shift by 3, and I'm going to take all of my y coordinates and I'm going to add 3 to them. And I need to do these in order. So first I'm going to multiply by 2, then I'm going to add 3. So let's go ahead and start here. So let's start with the point 0, 0. First, so that's number 1, I'm going to multiply by 2. So the x coordinate's not going to change, but the y coordinate is going to get multiplied by 2. Well, what's 2 times 0? 2 times 0 is simply 0. So that actually hasn't changed in this case. And after I'm done multiplying by 2, the x coordinate stays the same, and now I add 3. So this point, the y coordinate gets multiplied by 2, which is still 0, and then add 3. Let's do one more the long way. So now let's take a look at the point 1, 1. The x coordinate's just going to stay the same. Take this y coordinate but multiply it by 2. Well, 1 times 2 is 2. Take that new y coordinate and add 3, and that takes us to 5. So now this moves from 1, 1 to 1, 5. And can we fit another one on there? Let's find out. Here I have a y coordinate of 2. Multiply that by 2, and that's 4. Add 3 to that, and that's 7. The x coordinate doesn't change. And that is all I can fit on here. So now I do my best. And you can actually see the shape of the curve has been stretched vertically. It spans more vertical space in the same amount of horizontal space. And that's really what a vertical stretch does. All right, so in this case, y equals 0.4 f of x minus 1. So there's my first transformation, there's my second transformation. My first transformation, well, this is a positive value, so there's no reflection. 0.4 is less than 1. So this is what's known as a vertical compression. Now there's a couple of ways to say this, and unfortunately there's some inconsistency in the way that various textbooks, and I'm sure even with the way that various teachers represent this. So I'm going to backtrack a little bit. So before I call this a vertical compression, I'm going to say this is a vertical scaling by 0.4. Or you could call that 4 over 10, which is the same as 2 over 5. So that is correct. It's a vertical scaling, and vertical scaling means I'm just going to take the y value and I'm going to multiply it by 2 over 5. That's what vertical scaling means. There is another way to write this, which is to call this a vertical compression. But normally, or at least this is the way I was originally taught this, I would have called this a vertical compression by 5 over 2, because that makes a number greater than 1. Notice this number is less than 1, and I express a compression as a factor greater than this. But then if you write it this way, you need to understand that you are dividing by 5 over 2. And of course, multiplying by 2 over 5 and dividing by 5 over 2 is exactly the same thing. And then just to add to the pile of confusion, some textbooks that I've seen, and so because I see it in some of our own textbooks, some textbooks will write this as a vertical compression by, and once again, they'll just write it as 2 over 5, which once again brings us back to multiplying by 2 over 5. So that leaves us with some confusion which one to use. So what I recommend is, when you write this, my preference is that you're going to write this as compression. I want to see this word compression no matter what. And I'm going to trust that you know that compression means that it is getting smaller. And whether you create that shrinking by dividing by this number bigger than 1 or multiplying by this number smaller than 1, I'm afraid I'm just going to have to trust you that when you use the word compression, I'm going to trust that you're going to use it correctly. And if you don't use it correctly, then unfortunately marks will be deducted for that. So I'm sorry that was such a long explanation, but it fit there as well as anywhere. So that is the first part. The second part, thankfully, is a lot more straightforward because it is simply here. It's inside the functional bracket. So this would be a shift to the left or right. X minus 1, that means a shift to the right by 1. So that's the second transformation, is right by 1. So we can do the same thing we did before. Now I'm going to do it in the opposite order. I have a vertical asymptote at x equals 0. And it's going to be under transformation number 1. Let's try that again. Under transformation number 1, which is a vertical change, does a vertical change affect this line? No, it does not. So this just stays x equals 0. And then the second transformation is a horizontal change right by 1, so that changes that into x equals 1. I have a horizontal asymptote, which is at y equals 0. Does a vertical change affect this line? Well, it could, but it's 0. So what happens when we multiply this by 2 over 5? Or divide by 5 over 2? It doesn't actually change it. So it stays at y equals 0. And a horizontal shift does have no effect on this, so it stays y equals 0. So in terms of my graph, my horizontal asymptote is unchanged, and my vertical asymptote has shifted to the right by 1. Now I can take those other key points, for example, the point 1, 1, the point 1, 1. In the first transformation, it's going to, the first transformation is a vertical scaling. In this case, it's a compression. So 1, 1, the x-coordinate does not change, and the y-coordinate becomes smaller. It used to be 1, and we multiply by 2 over 5. And then the second transformation is a shift to the right by 1. So that gives me 2 over 5, which you might think of as 2, 0.4. So where is 2, 0.4? Here is 2, and 0.4 is, well, it's really hard to see. This point, 1, 1, was above and to the right of the vertical asymptote, or the horizontal asymptote and the vertical asymptote. So our new point is going to be around there. Now, what about negative 1, negative 1? The first transformation doesn't affect the x-coordinate. The y-coordinate becomes negative 2 over 5. And then we shift to the right by 1, and that becomes 0. And I'm going to write it as 0.4 right away. So where is 0? Here it is. And 0.4 is around there. I feel like I've done something wrong here. I dropped a negative, didn't I? Yes, I did. So that's supposed to be negative 0.4, which means that our point is over here at 0, negative 0.4. It's right there. And now I do my best. I'm just going to use that. The general shape has stayed the same. And so I'm really close to the horizontal asymptote right to start here. And I'm a little bit further away from the vertical, but I still get there pretty quickly. And I end up with a shape that looks something like that. It's really hard, I find, on the reciprocal function to even detect those vertical scalings unless you're very experienced and you have enough experience with them to see where it's coming in. So this one has been vertically compressed to achieve that. Okay, now we can get into some very strange stuff. So here I have this, it is a function, it passes the vertical line test, but it's not a function that we are prepared to describe using an equation, certainly not yet. But I do want to describe the transformations. So it's y equals negative f x plus 1 minus 2. I'm going to read it from left to right. So my first transformation is there, my second one is there, my third one is there. The first transformation is a vertical reflection because that's a negative value, but it's negative 1. So there's no scaling here. My second transformation is a shift left by 1. And my third transformation would be a shift down by 2. So now I can take all of these points and do each of those transformations to them. And what are these points? Well, I want to, just as I've done before, if possible, I want to go to my graph and find some good points. And those are points that land exactly on grid squares. So for example, negative 4, negative 4, negative 1 is one of those points. And I'm going to do this vertically this time. It doesn't have to be horizontal. So there's my first transformation. What does it affect? It's a vertical reflection. That means it affects the y-coordinate. And it's going to change negative 4, negative 1 into negative 4, 1. It essentially means multiply the y-coordinate by negative 1. What does my second transformation do? Second transformation shifts left by 1. That's going to take negative 4 and turn it into negative 5, and the 1 stays the same. And then finally shift down by 2, negative 5, and then 1 down by 2 becomes negative 1. So negative 5, negative 1. You know what? I'll put this one on because I started. Negative 5, negative 1. So there's the new location. Now you might think, oh, well in that case, it really just works out to be a shift to the left by 1. Don't fall into that trap. That's what happened here, but that's not necessarily what's going to happen throughout the whole transformation, and you're going to see that as we go. So let's do another point, which is this point, -2, 0. The first transformation is a vertical reflection. -2, 0 times -1, reflecting 0 just stays 0. Then we have a shift left by 1, -2 becomes -3. And then we have a shift down by 2. So the x-coordinate stays the same this time, and that becomes -3, -2. Let's find another good point, and that would be here at 2, 8. This time I'll go across horizontally. A vertical reflection turns that into 2, -8. Shift to the left by 1 becomes 1, -8. And shift down by 2 becomes 1, -10. And finally, our last point is 4, 8, which becomes 4, -8, which becomes, now I shift to the left by 1, that becomes 3, -8, and I shift down by 2, and that becomes 3, -10. And so I go ahead and do that. Now I've got a bunch of points to graph, so let's go ahead and graph those. So -5, -1, -3, -2, -3, -2, that's here. Now it's unfortunate because of my scaling. I think I'm going to have to change this question a little bit in the future, because 2, 8 is now at 1, -10. 1, negative, and unfortunately -10 is right there. A little bit off scale. And 3, -10 is also off scale. That's kind of awkward. I apologize for that. And so now I'm going to connect these. Fortunately, I've got a straight line tool that I can use. All right, so I connect those together. And now let's take a look at the original function compared to the transformed function. They still have the same shape, but you can see the reflection, you can see the shift to the left, you can see the shift down. And it's important that all of those transformations occur in the correct order. All right, this may be our last one. So, what is our first transformation? It's this number 2. That's going to be a vertical, and in this case, because it's larger than 1, it is a vertical stretch by 2, and that means I'm going to take the y-coordinate and multiply by 2. And then the second transformation, which is here, is down by 1. So, find some points. There's a point. There's a point. So we've got a bunch of good points to use. And this time, just as an exercise, let's try to do this without writing out all of the points and transformations. Let's just do the transformations in place. So in this case, we're going to get a vertical stretch by 2. That means the y-coordinate gets doubled. So this is the point -4, -4. If the y-coordinate gets doubled, that takes us to -4, -8. And then we shift down by 1. That takes us to -4, -9. -1, -1. So the y-coordinate, it becomes -1, doubled, -2 now, and shift down by 1 to -3. So what we're doing in this transformation is we're doubling the y-coordinate. So essentially we're taking the y-coordinate and doubling it, and then we're shifting down by 1. So the new y-coordinate is equal to the old y-coordinate minus 1. The new x-coordinate is just the old x-coordinate. There's no change in the x's. So what is the y-coordinate here? The x is going to stay the same. The y-coordinate's -1. Double that, it's -2. Shift down by 1. The y-coordinate here is 3. double that. Notice that there's nothing that stops us from going this way. Double that. Oh, we're not ready to write a point yet though. Double that to 6 and then shift down by 1 leaves us at 5. And then here the y coordinate is -6. Double that takes us to -12, and down by 1 takes us to -13. And once again, using the line tool here, I'm just going to connect these so you can see both the stretch, and it's harder to see the shift because the stretch dominates here. You can see that this new red graph is taller. It's harder to see the shift that's taken place, but it's also in there. All right, so I was wrong. It wasn't the last one. Here is a semicircle. So this is the top half of a circle, and here is the function that describes the top half of a circle. So that's an interesting function. It is a function, passes the vertical line test. Here are my transformations. I have my first transformation is a vertical compression. Actually, let's not call it a compression first. Really, that -0.5, the first thing we run into is the negative. So my first transformation is actually a vertical reflection. My second transformation is a vertical compression by, now I'm going to write this the way I was taught to write it. So if it's 0.5, I do 1 divided by 0.5, that's going to be 2. But the important thing here is that I'm going to take the y coordinate and I'm going to divide by 2, which is exactly the same as taking the y coordinate and multiplying it by 0.5. And the third transformation is a horizontal shift, and this one's going to be left by 2. So let's take a look. We've got points here. We've got -4, 0, which becomes, after the first, a vertical reflection. Well, that doesn't affect anything because it already had a y coordinate of 0. Then we multiply the y coordinate by 0.5, or we divide it by 2. That also has no effect. And then we shift left by 2, which is going to take -4 and turn it into -6. So this one takes this point over to here, to -6. All right, let's find, can we find another one? Well, there's a good point here. So this is the point 0, 4. So what happens to that? The first thing is we reflect it, so that becomes 0, -4. The next thing we do is we compress it by 2. So 0, -4 becomes 0, -2. And then the last thing we do is shift left by 2. So this becomes -2, comma, -2. -2, comma, -2 is right there. And then finally, the last good point we have to work with is here, which is at 4, 0. Which becomes 4, and it stays as 0 as we divide by 2. 0 divided by 2 is still 0. And that becomes 4, and now I'm sorry, the first thing was a reflection. 0 reflected is still 0 because that's multiplying by -1. Then it stays 0 because we divide by 2, or we multiply by a half. And then finally, 4 gets shifted to the left by 2, so that becomes 2, 0. So that is here. And so the curve has been reflected, which we can see, and that's a pretty awful rendition, but I don't know that I'm going to do any better. And so we can see this semicircle has been flipped over down to here, and also it's been squished vertically. So it's been squished or compressed this way. Okay, so that's it. I know that was a lot of examples. The only things you really needed were near the beginning. The rest of it was just illustrating it, and then here is your assigned work to practice it.